Let's talk about acceleration. Let's define acceleration by stating its formula. The formula for acceleration is the rate of change of velocity. So it's stated in this way, where acceleration is equal to delta v over delta t. The symbol capital letter delta, which is denoted by the triangle, it means change in. So delta v means change in velocity. Delta t means change in time. When we look at acceleration, we define acceleration as rate of change of velocity. We do not say rate of change of velocity per unit time, because the words rate of change already implies per unit time. So we just simply state it as rate of change of velocity. So what's the SI unit for acceleration? It's meters per second square, or meter per square second. Sometimes we can say it as meters per second per second. It means that it is the measure of how much meters per second is changing every second. So it's meters per second per second. The quantity is a vector quantity which carries both the magnitude and the direction. So let's study three kinematics graph that is associated with acceleration and how we can determine acceleration from there. In the first graph, displacement time graph. The displacement time graph, the S symbolizes displacement. So when we look at a kinematics graph, we basically look at the gradient and the area under the graph. The gradient of a displacement time graph basically tells us the velocity. What about the area under the graph? Basically, area under the graph means it's the product of the displacement and the time. Displacement times time does not give us a very meaningful physical quantity. So we're going to ignore this area under the graph for a displacement time graph. Now there are two lines, a blue and a red line. So what do they represent? We look at the blue line. It is a constant gradient. It has a constant gradient, means the velocity is constant. So if there's no change in the velocity, a constant velocity, it means that the acceleration must be zero, because acceleration is change in velocity divided by change in time. So change in velocity, 0 divided by change in time. So 0 divided by any number is still 0, so the acceleration must be 0. What about the red line? The red line carries a gradient that is getting steeper and steeper, means it's increasing gradient. It means that the velocity is increasing, and therefore it suggests that the acceleration is not zero. It's a non-zero acceleration. We'll look at positive and negative acceleration later, but we can tell that this acceleration is non-zero. Notice that both lines, blue and red line, both have increasing displacement. Let's look at the second graph. It's the velocity time graph. Again, the gradient of the velocity time graph gives us acceleration. The area under the graph gives us the change in displacement. So now we have again two lines, the blue and the red line. So what does the blue line tell us? It carries a positive gradient, so it must have a positive acceleration. The red line carries a negative gradient, so it must have a negative acceleration. Notice at this point, I would like to suggest that when we look at area, we can define negative area. Any area of the graph that is below the time axis, below the horizontal axis, is deemed as negative. So it carries a negative area. So naturally, those that are above the time axis would be positive area. So when we add them up, we literally just vector sum. A positive plus a negative area, we just add them up by vector sum. The third graph is the acceleration time graph. So again, gradient. The gradient of the acceleration time graph is the rate of change of acceleration, which does not carry a very practical physical meaning. So we're going to ignore the gradient. What about the area under the graph? It is the change in velocity. So when we look at the area under the graph, it is how much velocity has changed. Moving on, Now, let's look at a misconception that we have for acceleration. It is common to hear that some people just say that with positive acceleration, a moving object speeds up. When it's a negative acceleration, sometimes we call it as a deceleration. The moving object slows down. But is that the case? That is a misconception. Acceleration alone does not tell us if a moving object is moving faster or slowing down. We need the velocity of that moving object or the direction of motion of that moving object as well to determine if the object is speeding up or slowing down. Let's take a look at the following example. We have a velocity time graph profile of an object that is moving from negative velocity all the way to positive velocity. At this point, we notice that the gradient of this graph is constant. It is a positive gradient. Therefore, the acceleration, which is the gradient of a velocity time graph, is positive, and the gradient is constant. Therefore, it carries a positive constant acceleration. So we look at this illustration. We have a moving object that is moving to the left. By convention, we take rightward as positive. The object is moving leftward, so the velocity is negative. It is subjected to a net force that is moving to the right. And at this point, why do we use net force? We recall Newton's second law. Net force is equals to m times a. The net acceleration multiplied by the mass. So if the net force is moving to the right, means the net acceleration is also moving to the right. And in this case, by convention, it has a positive acceleration. Looking at the graph, which part of the graph is characterized by this motion? We would notice that the first part of the graph characterizes this motion. The velocity is negative. The acceleration, the gradient, as I mentioned earlier, is constant and is positive. And therefore, the object is actually slowing down. We can see that the value is moving from -5 to -4, -3, -2, -1, and finally, it reaches 0. So we can say that the object actually slows down, although the value, the velocity is increasing. -5 to -4 is an increment. -4 to -3, so it's getting bigger and bigger towards 0, getting less and less negative. But the sheer magnitude is from 5 to 4 to 3, so it is actually decreasing in magnitude, increasing in velocity. And the decreasing magnitude actually signifies that the object is slowing down. Moving on, after it reaches 0, it stops, but the force continues to be applied to the right. So it still exerts a positive acceleration on the object. And now, therefore, the object starts to move to the right, and therefore it carries a positive velocity. So this second part of the graph characterizes this motion. The velocity is positive, acceleration continues to be positive, and therefore the object seems to be moving faster and faster, because it's moving from 1, the speed 1, to 2, to 3, to 4, to 5, and so on and so forth. So we notice from here that the acceleration being positive does not mean that the object is speeding up. The first part of the graph actually shows the positive acceleration, but the object is actually slowing down. It does mean that the velocity is increasing, but it doesn't mean that the object is speeding up. It's actually getting slower and slower in the negative direction. Let's look at another graph. We have the same velocity time graph, but now we have a negative gradient. It means that the acceleration is negative. Again, we have this illustration. The box is now moving in the positive direction. The convention now takes left as positive, and the velocity is leftward, therefore it carries a positive velocity. The force now acts same to the right, but now it is deemed as negative force, and therefore it has a negative acceleration, which is what we have in this graph. The gradient is negative, and therefore the acceleration is negative, but the velocity is positive. So which part of this graph characterizes this illustration? It is actually the first part of the graph. Velocity is positive, acceleration is negative because it's moving to the right, when the convention states left as positive. And therefore the moving object is actually slowing down. The value of the velocity is decreasing towards 0. If the force continues to act on this moving object with a negative acceleration, now the object will have to change direction and start moving in a negative direction, which is to the right, and it's characterized by the lower section of the graph. Velocity is negative, acceleration is negative, the moving object speeds up. Because the value of the velocity moves from -1, -2, -3, it gets smaller and smaller in velocity, but in terms of magnitude, 1, 2, 3, 4, it's getting bigger. So it's actually getting faster and faster in the negative direction. So at this point, let's look at a common example that we use to illustrate this further. We have a ball that is thrown vertically upwards, and then it comes back down. Again, we take positive as upwards, and this ball is subjected to a gravitational field strength or acceleration due to gravity that is acting down. So g, acceleration due to gravity, is negative 9.81 meters per second squared. It's negative because we define by convention up as positive, so it carries a negative acceleration. So which graph, the first graph or the second graph, characterizes this projectile motion of the ball thrown up vertically and then come back down? It's actually the second graph, where it has a negative acceleration. So when we look at the path, the first part, the ball goes up, so it has a positive velocity, and then it reaches a velocity of 0 before it comes back down with a negative velocity. The ball actually speeds up as it comes down, which exactly matches the graph that we have earlier. So how do we change this projectile motion to fit the first graph we have? We simply change the convention to negative. And if this is negative, then what else needs to change? The upward velocity would be negative. The downward velocity would be positive. And the acceleration now would be positive as well, because it's coming down. And if this is the case, then it will be characterized by the first graph. So I hope this clarifies our understanding of acceleration